Around the year 100 CE, the Stoic philosopher Epictetus made a simple but powerful observation. He said that problems often do not lie in things themselves, they lie in the way we look at them. This idea has been used in science ever since. It appears in psychology, it appears in psychotherapy. The philosopher and psychotherapist Paul Watzlawick, in his classic work Change, distinguishes between two types of solutions: solutions that keep the same perspective and solutions that change the perspective. The first type tend to perpetuate problems. For Watzlawick, the key is always to step back, to reframe the situation. Now, here is my proposal. This simple, ancient, almost obvious idea can be very useful for physics. It can dissolve persistent problems. And it can do this without changing any equation, without changing any method, without changing any theory. We only need to change subtly how we organize our concepts. Let me show you how. I propose that we divide physics into three different perspectives. First, observational data. Second, the relations between data. And third, interpretations. The word perspective is important. It means these three parts must work in harmony, but they must also be somewhat independent of each other. The definitions of these three perspectives are simple, almost obvious. That is on purpose. The more controversial conclusions are just logical consequences of these definitions. So let me explain each one in detail. First, the data perspective. This is the most objective part of any empirical science. It is independent of the other perspectives, because the other perspectives depend on it. By objective, I mean the pure observational datum, not data that has already been interpreted by some model, just the raw facts. Second, the relational perspective. Its goal is simple: find relations between observational data. Use those relations to predict outcomes. From this definition, we get 5 characteristics. Let me list them carefully. 1. Because its goal is to develop relations that allow the determination of outcomes, it is fully confirmed when it achieves that goal. That is all that matters. 2. It is not a problem for this perspective if it is confirmed only on a certain scale, or only for a certain phenomenon. Confirmation can be local. 3. The relational perspective depends on the observational data it relates, but it is independent of explanation, meaning, or logic. The search for these belongs to another perspective. 4. Since relations are generally quantitative, mathematics is their natural language. They predominantly take the form of mathematical equations or methods. You put some data in, you get other data out. 5. This perspective is crucial for technology. Most technology depends only on this perspective. Now, here is a key point, a point that is often missed. We must distinguish between two things. First, the abstract mathematical relation. That is a formal object. It admits any values in its variables. It is pure mathematics. Second, the relation qualified by confirmation. This is what actually belongs to the relational perspective in physics. The qualified relation is not the bare equation. It is the equation plus the limits within which it has been empirically validated. Confirmation is always local. It happens on a certain scale, within a certain energy domain, for a specific type of system. The limits of confirmation are not an external appendix to the relation. They integrate it. They are part of what the relation is. A relation without its validity limits is not a reliable predictive instrument. It is a mathematical abstraction. It may be beautiful, but it is not yet physics. There has been a frequent error in physics. People present the abstract relation as if it were the qualified relation. They omit the limits. They forget to say where the equation was tested. This makes others assume the limits do not exist. That is a mistake, and it has consequences. Let me give you a formal description. In the real world, a phenomenon follows an unknown function. Call it f in red. The data relation confirmed within an interval, say r more than 0 and less than h, is merely a function f1 in blue. f1 coincides with f inside the confirmed interval r more than 0 and less than h. but it is not applicable outside that confirmation limit. Why does the limit exist? That question belongs only to the interpretive perspective. The relational perspective does not need to answer it. It only needs to respect it. The philosopher Nancy Cartwright has made a similar point. She argued that the fundamental laws of physics do not describe reality. They are tools, instruments. They work only under idealized conditions. She calls these scenarios nomological machines. Think about Newton's law of gravity. It only describes the motion of a planet if we artificially isolate the system. We ignore other planets, we ignore interstellar dust, we ignore relativistic effects. Outside that idealized context, the law lies. Not because it is false, but because it is being used outside the conditions where it was confirmed. This is not a defect of Newton's law. It is a feature of the relational perspective. All relations have limits. Now, the third perspective, the interpretive perspective. Its goal is to interpret the other two. It seeks an underlying mechanism, a model, a theory, something that explains everything. To do this, interpretation uses clues, not just the results from the relational perspective, but also apparent violations of meaning, violations of logic, and the limits of verification of relations. From this definition, we get several characteristics. Let me list them. First, interpretation can never be fully confirmed. No matter how well it interprets already known data and relations, a better interpretation might always appear. New data might conflict with it. New relations might challenge it. Interpretation is always limited to being better. It can never be definitive. It is not like a confirmed relation. It is a different kind of thing. Second, unlike the relational perspective, comprehensiveness is a qualifier here. If an interpretation only covers some relations, it is refuted by observations that contradict it. At least, it is refuted in the sense of seeking a single underlying fundamental mechanism. Third, interpretations are not merely quantitative. Quantitative relations belong to the relational perspective. So the language of interpretation is not primarily mathematics. It is logic, it is narrative, it is ontology. Fourth, interpretation cannot claim the merits of the relational perspective. The relational perspective came first. It is independent. The fact that an interpretation suggested a new relation does not mean the interpretation is confirmed. Only the relation is confirmed. This last point is subtle. Let me repeat it. If an interpretation leads you to a new equation or to the prediction of new data, and that equation or prediction is later confirmed, only the equation is confirmed. Only the data point is confirmed. The interpretation that suggested them may still be wrong. History gives us many examples. Now, let me explain how these perspectives depend on each other. The data perspective is the base. It is independent of the other two. The other two depend on it. No data, no relations. No data, no interpretation. The relational perspective is independent of the interpretive perspective. Interpretation does not change the relations. A relation confirmed in 1687 is still confirmed today, even if our interpretation of gravity has changed completely. The interpretive perspective, however, depends on both other perspectives. It must interpret both data and relations. You might object. You might say, but wait, relations and data are often discovered because of some interpretive assumption. That is the living history of physics. I agree. But here is the crucial point. Once a relation is established and confirmed, it assumes its own nature. It becomes independent of the interpretation that suggested it. The new relation is certainly a merit of that interpretation. Yes, it is a qualifier, but only that. The independence remains. The confirmation of a new relation does not validate the theory that originated it. It validates only itself. History gives us many examples. Newton's laws survived the collapse of absolute space and time. The equations remained. The interpretation changed completely. Ampere's and Weber's formulas were absorbed into a completely different conceptual framework. Maxwell did not throw them away. He kept the relations, he changed the interpretation. Bohr's atomic model provided precise results that remained even after the model itself was abandoned. The Balmer series is still the Balmer series, we just interpret it differently now. In all these cases, the relational perspective emancipated itself from the interpretive perspective that suggested it. This is not a bug, it is a feature. It is how physics progresses. So what changes with this division? The philosopher of science Ernest Nagel in 1961 identified three structural components in physical theories: an abstract calculus, that is, the mathematical formalism; correspondence rules, these connect theoretical terms to observational data; and a model or experimental interpretation. This is an important starting point. But Nagel's focus is the internal logical architecture of theories. My proposal is different. I am partitioning physical knowledge as a whole, not just inside a single theory. Nagel omits the data perspective. I think it is fundamental to empirical science. It deserves its own category. And Nagel divides my relational perspective into two parts: the abstract calculus and the correspondence rules. I believe this division is unnecessary. The abstract calculus is just one type of correspondence rule. Both belong to the relational perspective. But Nagel did identify something important. He saw that confusion between the predictive power of formalism and its ontological meaning is at the root of the realism-instrumentalism debate. Today, physics does not clearly separate the relational and interpretive perspectives. This causes many problems. The separation I propose eliminates those problems. It frees the relational perspective from the burden of having to explain itself. It frees it from having to make sense. At the same time, it allows interpretations to progress without fear. Without the fear that a new interpretation will affect already confirmed relations. Now, let me talk about dissolution. The physicist and philosopher Ludwig Wittgenstein introduced this term. He argued that philosophy does not solve problems the way science solves them. Philosophy dissolves them. To dissolve a problem means to show that the problem, as originally stated, was based on confusion, on a misplacement, on an improper mixing of concepts. Once we clarify the concepts, the problem no longer appears. Not because we answered it, but because the question loses its meaning. The simple separation of perspectives I am proposing allows the dissolution of several problems in modern physics, without changing any equation, any method, any theory. I will give you 4 examples. First, the division between instrumentalists and realists. Instrumentalists see theory as a predictive tool. They do not care if it reflects reality. Realists believe a successful theory should describe how the world really is. My 3-perspective division gives both sides reason, but within their proper domain. Instrumentalists are completely correct within the relational perspective. There, what matters are relations and predictions, not interpretations, not ontology. Technology depends almost entirely on this perspective. That is why it attracts most funding and most physicists. That is natural. But it is not the whole story. Realists are completely correct within the interpretive perspective. There, the search for meaning, for ontology, for a coherent story about the world is legitimate. It is valuable. It may even be necessary for guiding future research. The conflict dissolves because each claim operates on a different level. They are not competing, they are complementary. Let me briefly address a philosophical tradition: structural realism. Structural realism tries to find a middle ground between realists and instrumentalists. It responds to the pessimistic meta-induction. That is the argument that past theories were wrong, so current theories probably are too. The idea is to shift focus from unobservable entities to mathematical structure. What we know is not hidden natures, it is structural relations. There are 2 versions: epistemological structural realism, associated with John Worrell, It says we can only know structure, not nature. Ontological structural realism associated with James Ladyman. It goes further. It says structure is all that really exists. There are no objects with intrinsic properties, only relations. Then there is the Newman problem, a devastating critique. It says that claiming we know only structure is trivial and empty. Unless we already assume the world is carved into natural kinds, pure structural knowledge tells us nothing. The logic is as follows. For any set of objects, if we only know their number, their cardinality, we can always artificially define a structure that relates them to satisfy any formal description. So saying the world has structure X becomes a merely logical truth. It gives no information about physical reality. How does my proposal differ from structural realism? I do not try to solve the Newman problem internally. I dissolve its force. The Newman problem only applies to the pure relational perspective. And there I agree. The relational perspective alone is trivial. That is why I call it instrumentalist. It does not pretend to give the final word on reality. When we move realism to the interpretive perspective, realism does not need to win on mathematical structure. It reigns in its own domain, narrative, ontology, the search for understanding beyond mere prediction. The Newman problem is a problem for those who try to make structure meaningful by itself. I propose that structure has no intrinsic meaning. It gains meaning only in interpretation. So my diagnosis assigns the Newman problem a restricted domain, the relational perspective, which never claimed to provide truth about reality, only predictive power. Instrumentalists often say interpretations and philosophy are useless in physics. This is clearly a mistake. Yes, economic value is concentrated in the relational perspective, but interpretive models give relevance to data and relations. The same datum or relation can point in a wrong direction, be irrelevant, or be deeply revealing. It all depends on the quality of the interpretation that frames it. Interpretation has a greatly underestimated strategic value. It is what often launches physics to a new level. New interpretations suggest new experiments. New experiments reveal new data. New data demand new relations. The relational perspective does not exist in a vacuum. It is guided historically and heuristically by interpretation. But once confirmed, it stands alone. Second example, renormalization. Quantum electrodynamics returns infinite values for the mass and charge of the electron. To solve this, physicists subtract the infinities. That is renormalization. Critics say this makes no logical or mathematical sense. And yet, when applied, the equations return extremely precise predictions. Some of the most precise in all of science. The conflict between efficacy and meaninglessness disappears when we place renormalization in the relational perspective. In the relational perspective, the only goal is predictive efficacy. Explanation is another perspective's task. So, renormalization is not a problem in the relational perspective. It is a method that works. That is enough. The mystery remains, of course. Why does subtracting infinities work? That question belongs to the interpretive perspective. There, renormalization becomes a clue, an invitation, not a contradiction. Third example, the vacuum catastrophe. Quantum field theory is extremely precise at atomic and subatomic scales, but it fails dramatically at larger scales. Here is a famous example. The predicted vacuum energy inside a coffee cup would be enough to evaporate all the water in Earth's oceans. Not once, billions of times. This has been called the worst prediction in the history of theoretical physics. Now watch what happens when we separate perspectives. The cause of the catastrophe becomes simple. It is using a relation outside its limits of confirmation. The relation was confirmed at certain scales. It was never tested at the Planck scale. Extrapolating it there is not a failure of physics. It is an error in application. The error is not in the equation. The error is using the equation without the qualification that confirmation provides. In the relational perspective, the correct relation is not the abstract equation. It is the equation plus its empirically confirmed limits. The vacuum catastrophe is precisely the use of the relation alone, ignoring the limits, extrapolating to an energy scale never tested, and getting nonsense. The problem dissolves when we respect that relations have limits. This is not a mystery, it is a reminder. Fourth example, the quantum measurement problem. Quantum theory says the probability of outcomes is given by the Schrödinger equation. But when we observe or measure, that equation collapses to a single outcome. Interpretations of this collapse fall into two groups, ontological and epistemological. Ontological interpretations say the wave function is real. Collapse is a physical event. This requires explanation. What triggers collapse? What counts as a measurement? These are difficult questions. Many solutions have been proposed. Copenhagen, objective collapse, many worlds. None is universally accepted. Epistemological interpretations, like cubism, say the wave function is a state of knowledge. Collapse is just information update, no mystery, no physical transition. But cubism has a problem. It becomes subjective. The update depends on the observer's expectations. Subjectivity is a problem for science. Science aims for objectivity. Also, cubism still needs to explain coherence between different observers, so it does not fully eliminate the problem. Here is my proposal, based on the three-perspective distinction. If we place the mathematical equations of quantum mechanics exclusively in the relational perspective, we isolate the results from the interpretations built on them. We then see that these equations constitute a probabilistic method. Their collapse upon observation follows from the method itself. It is characteristic of probability. Just as it makes no sense to integrate a function at a point where it is discontinuous, probability makes no sense at the point where the outcome is already known. Probability is a tool for reasoning under uncertainty. When uncertainty disappears, probability collapses. Not because of a physical process, not because of a subjective update, but because the conditions for applying probability are no longer met. So, quantum phenomena still require interpretation. The wave function still requires interpretation, but the collapse does not. Collapse follows from the probabilistic method, not from something underlying in nature. This view depends on no interpretation. It is a feature of the method, of the relational perspective alone. It does not mean anything about the real world. It is not subjective. Even if observation involves an update of knowledge, it does not depend on the observer's personal characteristics. Any observer in the same conditions, at the same place and time, will see the same result. Let me illustrate with Schrödinger's cat. With my proposal, the cat is always logically either alive or dead. That is a fact about the world, not about the observer. Any observer who does not know the real state can calculate probabilities. That is the relational perspective at work. But once an observer knows the real state, by opening the box or observing vital signs, the probability calculation immediately loses meaning. It collapses. Not because the cat's state changed, but because the observer's epistemic situation changed. Collapse is not a physical event. It is not a subjective projection. It is the logical consequence of acquiring information. Probability applies only to unknown outcomes. When the outcome is known, probability is no longer applicable. The measurement problem is dissolved. It ceases to exist. Interpretations may still be correct by coincidence, but they are no longer necessary to explain collapse. Now let me introduce a new concept, one that is not in the standard literature. I call it half-truths. A completely false concept rarely survives, especially in a critical environment like science. It is too weak, it is detected, it is discarded. But when a false concept is joined with a true concept, a new concept forms. I call this a half-truth. The half-truth borrows the strength of its true part. It becomes credible, it persists. But it also carries the false part. That false part then contaminates every concept built upon it. Half-truths are harder to detect than outright falsehoods. They feel true. They are partly true. That is why they propagate. To detect half-truths, we must break all concepts into their independent parts. Separate what is true from what merely seems true. Test each part individually. The confusion between relational and interpretive perspectives, I suggest, is a half-truth generator.
A confirmed relation is true within its limits. That is the true part. But when that relation is presented as if it also implied a particular interpretation, the interpretation is not confirmed. It is carried along by the relation's strength. That is the false part. Many debates in physics persist because both sides are defending half-truths. Each side has captured part of the truth. Each side has also inherited an error. The separation of perspectives allows us to cut these half-truths apart. Let me conclude. Assume both these premises are correct. Premise 1. The three perspectives, data, relations, interpretation, are conceptually separable. We can distinguish them. We can analyze them separately. Premise 2. To detect and avoid half-truths, we must separately analyze everything that is separable. It follows that dividing physics into these three perspectives is not optional. It is necessary, at least at the analytical stage. Failing to separate the relational and interpretive perspectives causes many problems. It spreads half-truths. Let me list 5 examples. First, interpretations are often validated by the merits of relations that preceded them, relations that are independent of them. This allows errors to become dogmatic. A bad interpretation can survive for decades because it is attached to a good equation, or because it successfully predicted an observation that was later confirmed. In both cases, the confirmed element, equation or data, lends its strength to an interpretation that does not share its epistemic status. Second, confusing the two perspectives demands meaning from the relational perspective. But meaning is not its job. At the same time, this confusion denies any utility to interpretation. Both perspectives are harmed. Third, this confusion leads to the mistake of thinking mathematics is the language of all physics. It is not. Mathematics is the language of the relational perspective. For interpretation, logic is the more appropriate language. Narrative is the more appropriate medium. Fourth, not separating the perspectives creates a false fear. A fear that changing interpretation will change confirmed relations. This prevents the improvement of interpretations. Physicists become conservative for the wrong reasons. Fifth, confusing the confirmed relation with the abstract mathematical relation leads us to omit the limits of confirmation. We treat equations as if they were universally valid. Then we are surprised when they fail. Observe this as well. The relational perspective and the data perspective attract most economic interest. That is fine. Technology is important. Prediction is powerful. But the relevance of data and relations also depends on the quality of their interpretation. A datum without interpretation is just a number. A relation without interpretation is just a formula. The interpretive perspective likely holds a greatly underestimated strategic relevance. Its diffusion may not be as universal as that of the relational perspective, but this is not a weakness. It is a consequence of its strategic nature. What is strategic is often less visible by design. That does not make it less important. Philosophy has always defined itself as the struggle to separate what is true from what merely seems to be true. Its role is to unsettle indistinction, to distrust easy fusion, to suspect unexamined unanimities. If the interpretive perspective has the strategic value I have suggested, and I believe it does, then the insistence on calling it useless deserves scrutiny.
That insistence may be just an inertial cultural bias, but it may also function as a veil that protects the territory of those who benefit from it. To raise this hypothesis is not to delude. It is to recall something. When a discourse declares a distinction useless, the distinction between what is and what seems, philosophy asks a simple question. Who does that uselessness serve? This hypothesis will not dissolve all half-truths installed in physics by itself, but perhaps it can serve as a small eye-opener. Perhaps physics, in rediscovering philosophy as its old ally, will also recover the courage to ask questions, and to go even further. Before I go, let me add a personal note. What you have just heard is a small part of a much larger body of work, a work I have been developing for over 40 years. I describe this work in full in my book, which will be launched soon. You can find the link below. If you wish to contact me or to learn more about my ideas, please visit my website. Thank you for watching. This content is original and created entirely by me. The avatar you saw and heard is a digital replica of me. He cloned both my voice and my appearance. My digital avatar was used to improve the presentation within the resources available to me. This video is my entry for the Core 1 competition in the Philosophy of Physics category, an initiative by Theories of Everything with Kurt Mungle. Thank you. Goodbye.